All right, good afternoon, everyone. I'm going to get started. Welcome. As you probably guessed, this is Building Microservice Architectures. I just came back actually from a conference in Boston, the first O'Reilly Software Architecture Conference, and almost half the sessions there were about microservices in one way or another. This is insanely popular, and a lot of people are doing it, going headlong into it without fully understanding the pitfalls. And so I want to talk about, get to the root cause of why this is so insanely popular as I go along here today. So what I'm going to talk about here today, first I'm going to talk about some definitions. One of the tricky things anytime you talk about architecture is getting the right context in place to understand enough of what you're talking about to make sense of it. So I'll talk about some definitions that are pertinent in this microservice world, including some things like some code metrics that you can use as an architect to, as I suspect, many of you are in the situation of taking a monolithic application architecture and decomposing it into a services or microservices architecture. So I'll talk about some metrics and tools that allow you to do that. I also talk about the specific problem that microservices are trying to solve. This is not the end-all cure cancer, one-size architecture fits all problems kind of solution. There are very specific things it enables you to do, and it fixes a particular interesting problem that we've had a long time in architecture, and so I'll talk about what that is. Then I'll talk about some characteristics of microservice architectures, in particular in contrast to monolithic architectures, and then a bunch of engineering practices. It turns out that is one of the defining characteristics of microservice architectures is you have to pay a lot of attention to the engineering practices around both development and operations unless you want to create a kind of a train wreck. So let's talk about some definitions. And the first one I want to talk about is a concept that comes to us from domain-driven design by Eric Evans. Domain-driven design is ostensibly an object modeling technique where you are supposed to take ideas and then decompose them into domains and then think about how domains communicate with one another. The implementation book over here by Vaughn Vernon is quite good in reifying these very abstract concepts into something closer to software concepts. But there's one idea in domain-driven design in particular that's quite important in this microservices world, and it's this idea in domain-driven design of a bounded context. So one of the things that domain-driven design defines is that when you define a domain boundary, like customer, for example, it is its own bounded context, meaning that the things within the customer domain know all the intimate details of how things work, but nothing outside that customer domain knows any of those details. They can find out by doing some sort of messaging or something like that, but the internal details of how that thing works are completely encapsulated. Now, domain-driven design is a logical construct. It is a modeling tool, but what we're doing in the microservices world is reifying this concept of bounded context and putting it into practice. And so when you look at a microservice, it really does meet this bounded context idea, both logically and more importantly, physically. So when we create a microservice, it is completely encapsulated. So if it needs persistence, that's encapsulated inside the microservice. Everything that it needs in its life is encapsulated inside it, and it meets this bounded context idea. And it turns out that's one of the defining characteristics of microservices, and the reason why is that is what gives microservices their superpower. And I'll talk about their superpower in just a second. The next definition I want to talk about are some coupling metrics, structural coupling metrics in code. And two in particular that I want to point to here. For any code artifact that you have, this could be a package or a namespace or it could be a class, the afferent coupling to that class are the number of incoming connections or references to that class, and the efferent coupling is the number of outgoing connections. And the easy way to remember this, because these are very similar words, is that efferent coupling, the outgoing connection, starts with the same first letter as the English word exit, and so that's how you know those are the outgoing ones versus the incoming ones. This is an interesting metric for us to track because we care a lot about coupling metrics in this world, particularly when you're starting to look at architectural characteristics of code. Structural coupling is one of the interesting things that you want to look at from an architectural standpoint. And there are some tools out in the world that allow you to look at structural coupling in a variety of different ways. Some of these tools were inspired by very old school Smalltalk tools. There was a really cool tool in the Smalltalk world called Code Crawler, and X-Ray is an implementation of this in the Java world. This is a little tricky to see because this projector has stunningly bad contrast. But basically, this is a code base. The lines that you see here are inheritance lines. There are lines between these guys. The boxes represent classes. The length of the box indicates the number of lines in the class. The width of the box indicates the number of methods. But the interesting thing for us is that when you click on one of these guys, it will show you its afferent and efferent coupling. There are more lines here. You just can't see them very well. But the weight of the line here indicates the strength of the coupling between these two classes. And so what that suggests is if you wanted to pull these two classes apart, ones with really bold lines between them are going to be harder to pull apart because they have more coupling points between those two classes. The more useful view in X-ray is this kind of pie chart view. And again, it's kind of hard to see because the contrast is shockingly bad in this projector. But there are actually a spider web of lines here. The only one you can really boldly see right here. But the point of this is, you can see this a little better, is that there are definite patterns in the way that these structures are coupled together, and you can use that patterning to start thinking about how to pull them apart. I'll show you one that's so dense you can't avoid seeing the lines on it here in just a second. This is a class dependency, and one of the problems you run into is the hairball effect, where you start getting too many lines overlaid on top of one another. And X-ray will let you attack that. That's package dependencies. Here is Azurus, which is an open source BitTorrent client. And there's a whole lot of coupling going on here. But you can also filter these down, which is really useful in any kind of visualization tool like this to avoid the hairball effect. Filter it down so that you just see the really important connections that exist. It's going to be interesting to see what this looks like. This is from a real monolith that I did some work on. Yeah, you can't miss the lines on this one. This is from an actual project that I've been doing some work on, and no matter how bad the contrast is, you can't miss it here. This is the package level coupling on this project. The class level coupling actually crashed X-ray, which is quite difficult to do, but they managed to do it. But even in this hideous mess, if you squint at this and look at it like an impressionistic painting, you definitely see hot spots here. You see a definite clustering up here and a different clustering down here, and that's really the structural hot spots within your code base. So if this were your monolith and you wanted to break this down into a smaller and smaller set of services, decompose it, eventually maybe into a microservice architecture, notice that when you look at each one of these packages or classes, the more red lines you have to snip, the harder your job's going to be. And the bolder those lines are, the harder it's going to be to snip them. And so you can look at this structurally and start thinking about, okay, what's the least structural friction that I'll get as I start pulling this apart? In this combination, how many things will I have to break? And so it's a very coarse-grained kind of tool, but I'll show you how you can use this to kind of right-size your decomposition a little bit later on. These two metrics are really interesting to us because software architecture always represents the tension between coupling and cohesion. If you think about the first kinds of applications anybody built on mainframes where the data and the code and everything resided in one big memory space, that's all cohesion and no coupling. As soon as you start pulling things apart and making them communicate with one another, then you start talking about coupling as an interesting characteristic in software. And that is, in fact, one of the interesting things that microservices do to us from an architectural level. Because microservices promote coupling from application to integration architecture. Here's what I mean by that. When you look at a monolithic application that consists of a whole bunch of classes that communicate with one another, you don't really think much about how they communicate with one another or how long it takes for them to communicate with one another for method calls. So you don't worry about, there's a method in here that makes a method call on this other class inside a loop and does it a couple of hundred times. It's no big deal. But when you take this monolith and decompose it into a set of services, now you have a much coarser grained kind of connection between those services. Now each of these services still has classes and methods and all that stuff inside it, but the way that they communicate with one another now is part of integration architecture, not application architecture. There's a famous document that I'll point you to. I don't have it on my slide, but I'll point you to, called Peter Deutsch's The Fallacies of Distributed Computing. This document's been around for about 20 years now, and it's all the mistaken assumptions people make when they start distributing things. The mistakes like that latency will be 0 and that all the machines will actually be up and available and running and ready to accept calls, and these are all mistakes people make. And this is another one of those mistakes people make that you've got to now start thinking about. What do those messages look like just being passed between these microservices, because now this is part of my integration architecture, no longer internal to my application architecture. And so you have to be really explicit about coupling here and think about how things are coupled together. One of the ways that we build protections into these kind of architectures are with specific engineering practices. I'll talk about consumer-driven contracts in a bit as to how you can manage the collaboration between these services. It forces a coarser grained coupling than you have if you have application architecture. You have to think more carefully about what kind of information is passed back and forth and things like aggregate and composite information, how you want to handle that. If you have really undisciplined coupling in a microservices architecture, you get a real mess. The classic anti-pattern here is you have a tool that lets you right-click and create web service, and boom, create 1,000 of them, and you've created an anti-pattern called a spider web architecture where you can't really figure out what's going on anymore. And now your coupling dynamics have become an integration issue, not just an application architecture issue. And so you have to think a lot more carefully about how things are coupled together in one of these worlds, because now this is a lot more of a first-class citizen in this kind of world. And we'll see that as we start talking about the characteristics of microservices directly. The next concept, definition kind of thing I want to talk about is ACID versus base. We've all been fat and happy using ACID transactions for a few decades now, and we all love those. And our business users, in fact, love them in an unnatural way. Love them too much, in fact, because most of the world's not really transactional. So we all know what ACID means: atomic, consistent, isolated, and durable. This is one of the magic superpowers of relational databases. They give you this thing pretty much for free. But more of this services and microservices world is much more of the base kind of world: basic availability, soft state, and eventual consistency, where you don't guarantee transactions across machines, but they will eventually become consistent with one another. One of the things that drives base over ACID is this observation that as you get a certain number of distribution for your data, as you get more and more users and more data, and you are inevitably required to distribute it more and more ways, you reach a certain point where you can no longer guarantee the ACID properties that you get from relational databases anymore. This is what's known as the CAP theorem. There's a mathematical proof here that once you reach a certain level of distribution, you can no longer prove ACID. And so that's why all big systems ultimately have to succumb to doing base and eventual consistency rather than doing ACID transactions, because once you hit a certain scale, you just literally can't do it anymore. But this is actually a good thing for us, because we've sold our users on this idea that transactions are just as free as the air and you can have all sorts of transactional behavior in your applications, even things that don't really happen in the real world. One of my colleagues several years ago famously made the observation that your favorite coffee shop does not do a two-phase commit. When you go to Starbucks, you pay them money and you get a receipt, but you walk to another part of the store before you eventually get your coffee. That's eventual consistency. What if Starbucks actually did a two-phase commit? You would hand them their money and they would hand you their coffee and you'd both let go at exactly the same time. That's a two-phase commit in a coffee shop. So why don't coffee shops do that? Wouldn't it make you feel better as a member of the coffee buying public if your coffee shop did a proper two-phase commit? The reason they don't do that is because it's screamingly inefficient to make one person handle all this stuff, and so they distribute it and they do eventual consistency. The classic example that everyone uses about transactions is always banking stuff. But you know, no ATM on earth actually does a two-phase commit for two reasons. One is they're all designed to work in offline mode in case their connection to the mothership has been snipped for some reason. They can still work for a while and still distribute money. The other reason is no one wants to stand in an ATM for 6 or 8 or 10 minutes waiting for some batch job to run on a mainframe somewhere, which is where your bank records still actually live, which is why banks still do reconciliation runs at 2 a.m. every morning. You know, banks existed before computers existed, and used to bank records traveled on horseback, and there is no two-phase commit when a pony's involved. We've got to get our users away from this idea that transactions are a free thing, because almost nothing in the world really acts transactionally. And we've given this to our users for free for a long time because we've had monolithic architectures and because we've had big, giant relational databases. But this is one of those capabilities that goes away in this microservice world, and we have to find better ways to solve this problem. Now, some things, as much as you want to resist it, are going to be transactional, and we can handle those things, but we want to handle those as a special case, not the way the entire universe works, because the entire universe really is not a transactional thing. So those are all definitions about things. Let's talk about the problem we're trying to solve here. Software architecture is always a reaction to constraints that you're trying to build things around. Architecture and engineering are kind of reactions to constraints. And the constraint that we've been chasing for the last 20 years or so seems to be scalability, because we started out on local machines, then we moved to client-server architectures, and then quickly to 3-tier to get scalability, and then to web, which is a whole other scalability challenge, and then enterprise-level web and more scalability for web. And so we built a lot of architectures that try to solve this problem of using shared resources really effectively. We've never really had enough resources for a long time, and so we build architectures to try to take advantage of those. That's why you have things like application servers that can create thread pools and database connection pools and pool all those resources together. And this is what leads you to architectures that look like this. Things, went too far there, sorry. That's what leads you to architectures that look like this, with things like application servers and enterprise service buses. And this makes perfect sense logically on paper, because there's a certain common behavior that each one of these services needs to have. Why not just put that in one nice place? There's a goal in architecture to create single sources of truth for things. Data people like to do this, but architects like to do this too. Let's create the single customer service can handle all this stuff, because it makes logical sense to have all that code in one place so you don't risk duplication. It's nice and dry, so there are a lot of driving forces for that. The problem with that, though, is that yesterday's best practice is tomorrow's anti-pattern. We build these architectures around constraints that exist, and then those constraints disappear, and all we're left with are the architectures that reflect those constraints. I'll give you a good example of this. Probably everyone's first experience with transitive dependency and how much fun it can be is the DLL hell problem in Windows. For a long time, you had to worry about dynamic link libraries overriding other ones because they were newer. But think about why that architecture existed. The first versions of Windows had to run on really limited hardware and very limited hard drives. They didn't have enough hard drive space to statically link all those files, and so they created this architecture. The limitation on hard drive space disappeared after a few years, but the constraint in that architecture lasted for a few decades, because once it's in place, it's hard to get rid of. But let me give you a more current example of this. We have a client based in Europe that runs an airline, and their architects, excuse me, had built a really nice architecture where everything the airline knew about customers is in one big place, an application server, clusters, and that was represented by clustered relational databases. Everything looked really good. And then a volcano blew up in Iceland. And pretty much every customer of this airline that had a ticket called up their customer service center, certainly in Europe, and said, hey, is my flight going to be affected by this volcano going off in Iceland? The problem is they had people trying to board airplanes in Singapore that couldn't board their airplane because their customer service was slammed because everything was one big bottleneck. And as soon as the customer support guys started hammering on the customer table to find out, has this person's flight been affected, people couldn't board airplanes half a world away because everything was too coupled together. So one of the things that we've realized here is that architecture is really an abstraction until you operationalize it. That sometimes the instincts of architects to build single sources of truths, while logically and conceptually a really smart thing, is a disservice to the business because it cannot withstand events that will happen in a realistic business context. In their case, they would have been better off if they had a little bit of duplication across customer service for boarding airplanes and customer support, but their architecture had survived this problem. So this is one of the things that we're looking at in microservices, is to make change less expensive. And really, this is a variation of service-oriented architecture. And in fact, service-oriented architecture's got a bunch of stuff right. They're the ones who started thinking about breaking monoliths down into services. They're the ones that started focusing on integration over internal coupling and how to solve those problems of versioning endpoints and things like that. And they're the ones who started this trip for base versus ACID. But they also missed a few things. One of the things they missed is that architecture is abstract until it's operationalized. You build these really exuberant architectures with single sources of truth, but then it's very hard to make changes in those architectures. You can't change a single piece because this piece is so coupled to everything else because you're trying to share all those resources everywhere. The other thing that traditional SOA missed was the impact of Conway's Law, which is about team structure. And I'll define that and talk about that impact in just a second. And the other thing traditional SOA missed is the folly of trying to build Uber services. Architects always want to build single sources of truth for things, but sometimes that's not the right thing to build, and we're learning that more and more. And the biggest thing that traditional SOA missed is it didn't support easy change. Change is very expensive in one of those worlds, and that, in fact, is the driving characteristic of microservices. That is the main benefit you get from microservices, is this is really the first architectural style that supports change as a first-class citizen. We've long defined software architecture. One of the definitions is literally the things that are hard to change in your ecosystem. But because we pay attention to the operationalization of the architecture as part of the design of the architecture, change is easy and in fact expected in a microservices world. This is really the defining characteristic of microservices, is that make change much less expensive and in fact encourage change at the architectural level. The other interesting thing about microservices, and one of the reasons I think it's so popular right now, is this is the first post-continuous delivery architecture. It's the first architecture that fully embraces all the things we learned about DevOps and operations. It's the first architecture that takes all those things into account as a first-class citizen. All architectures going forward are going to have to do this because you can't ignore all those operational concerns. This just happens to be the first one to do it and do it well. So that's the problem we're trying to solve. Let's talk about some characteristics of these kind of architectures. And I want to start by talking about Conway's Law. This is an observation that Melvin Conway made back in 1968. No, way too fast. There. That organizations which design systems are constrained to produce designs which are copies of the communication structures of those organizations. Besides being needlessly wordy, Melvin Conway observed here that when you have a communication structure within an organization and you're building technical things, the technical things will end up having the same tiers as your communication structure in your organization. What this means for software is that if you have a bunch of specialists running around, like UI specialists, middleware specialists, and DBAs, you will end up with those layers in your architecture because it's just a natural kind of way communication flow works over here. It's going to end up modeling and resembling the same thing over here. And this is one of the really interesting things about microservices. Now, you don't have to do this to do microservices, but a really common characteristic of these kind of architectures takes advantage of Conway's Law. A lot of us within ThoughtWorks believe really strongly that Conway's Law is a powerful force in organizations, but it can be a force for good. And so rather than organize teams like this, where you put all the like people together, a really common thing to do in this world is to create domain-specific teams, these cross-functional teams. This is something that we refer to as the inverse Conway maneuver, of taking Conway's Law and saying build teams that look like the architecture you want, and it's therefore easier to build those architectures. Because now you're not building a communication structure that's counter to the kind of architecture you're trying to build, which is difficult. If you make those two things map to one another, it's easier. In fact, we have two names for this. One of them came up with by an enterprise architect, and the other was just a regular guy. And so the inverse Conway maneuver is one of the names, and domain architecture isomorphism is the other. So which one do you think the enterprise architect came up with? But this really is domain architecture isomorphism. It's a mapping from the domain to the architecture to make that communication structure a lot easier. When you talk about technical characteristics of microservices, what we're really talking about here is breaking a monolith versus microservices. So we're very familiar with monolithic application architectures. We have multiple things running inside a container of some kind. When you want to scale those things, you get multiple containers and you have some sort of protocol that allows you to cluster them together and pass communication back and forth. The microservices world, though, very much views this more in a Unix or Linux philosophy where each service is its own process and it owns everything about itself. And so you have these little processes that run to handle requests. And in this world, you scale these things by spinning up more versions of processes. And so here's one of the first differences in this style of architecture, because over here, all this clustering and all this other stuff is really the concern of kind of the application servers and application architects and all that stuff. Whereas here, things like scalability is purely an operational concern. That's actually good because as an architect, I shouldn't really care about scalability. If scalability is kind of automatic because my operations group does it for me, then I don't have to worry about that, and I don't have to build places in my architecture to accommodate that kind of scalability. So this actually, because operations and DevOps is a first-class citizen here, we can use the tools that they have to handle scalability rather than having to build it into our application architecture itself. Here's where this Conway's Law business really kind of a good example of where this is kicked in. So in this world, you think of products versus projects. So the kind of anti-pattern of projects in big companies, you get a team of developers together, and they work on something, and they finish it, meaning that it's whatever its ship date is. They pass it off to someone in operations, and then operations takes over for it, and then this team of developers disbands and goes off and starts working on something else, maybe another project or something else, maybe it's the same team or a different group. The problem with this is this poor guy in operations now has a hard time getting maintenance and enhancements and all those things done on the things that are already running in production. Amazon has been a big leader in this world, and they have a different perspective on this. They've implemented this inverse Conway maneuver, and they build products and not projects. And the perspective shift here is that at Amazon and companies like that, they're doing the inverse Conway maneuver, they have these little cross-functional teams. They refer to these as two pizza teams. So at Amazon, no team shall be larger than can be fed with two large pizzas. That's the philosophy here. And this is actually based on something that's really old. Back in 1975, Fred Brooks wrote the Mythical Man Month. And he figured out what the optimum size for a software development team is like 8 to 12 people. Because once you get higher than that, then the amount of communication overhead between team members becomes more than 50% of the time that you spend on the project. So Amazon read that and kind of took that to heart, and they built these cross-functional product teams. Cross-functional meaning that it has developers and business analysts and QA people and operations people on it. There's an operations person that's a permanent team member here because this team is the one that's responsible for putting their service into production. And they don't hand it off to somebody. They own this thing forever. They never end. This is the product that they work on. This is what they do as part of their job, is build this product as part of the ecosystem. That has a couple of interesting side effects as well. One is you have a product owner that goes and advocates for this product to be reused within other parts of the ecosystem. So in Amazon's example, maybe you own the New York Times bestseller service. You might, as the product owner, go to other pages within Amazon and say, hey, what would you like to see new on this New York Times bestseller microservice? The other interesting side effect of this is it makes things like social contracts a more viable part of your software development. For example, let's say you're in a traditional siloed organization and some of the code that you've written blew up in somebody's face in the middle of the night, and someone from operations got paged and they had to come in and fix some sort of train wreck that you created inadvertently a while ago. And maybe you get an email the next morning that says, oh, by the way, this code you wrote 2 years ago got somebody up in the middle of the night. You go, wow, it must really suck to work in operations here. Let's see if I can create another catastrophe today. But if that person was part of your team and they got paged at 3 a.m. and the next morning you have to look at their sad, tired eyes over breakfast, it's going to make you a better person and a better developer, because now there's a social cost to the mistakes that you make when you're working, rather than just some sort of abstract something that will affect somebody else. It's a member of your team now. This 12 number is not coincidental. I think that's the size of pre-verbal hunting parties. Most sports teams are about that size. This is a natural constant for people, and so we're trying to leverage that as much as possible in this world. So let's talk about a couple of prefer things. The Agile Manifesto, one of the clever things that it did was say we prefer the thing to the left to the thing on the right, which is not to say the thing on the right has no value. We just like the thing on the left more. And I have a couple of those here around architecture stuff. And one of those is prefer choreography to orchestration and when you're doing integration architecture. Let me explain what I mean by that. So in the traditional kind of orchestration world, this is the traditional service-oriented architecture in the enterprise service bus kind of pattern, you have these services and they communicate through each other through an enterprise service bus, which also has additional responsibilities. It does things like surface orchestration, figuring out which services belong to one another. It also does things like routing and transformation, so it'll transform data between one service and another, so you don't have to worry about that on a service-by-service basis. This, again, is toward that idea, this observation by a bunch of architects that, hey, you know, this service has to worry about the data format of this other one, and all these guys have to worry about data format, so why don't we just create a single thing to handle all this data format stuff with this enterprise service bus thing in the middle, good to go. It makes perfect logical sense. This is called the orchestration style because it's like you have a conductor of an orchestra, and anytime one of these services needs to do something, they check with the conductor to make sure it's okay for them to do that. In the microservices world, we prefer the choreography style of integration architecture over the orchestration style. And in the choreography style, these services are completely self-contained, and if they need to communicate with another service, those two service teams get together and figure out exactly what sort of stuff they need to pass back and forth with one another. They don't have to check with any third-party arbiter. In fact, nobody else is concerned and involved in this conversation at all. The motivation for that, and the reason that we do that in this world, is that we're really trying hard to honor this idea of a bounded context. And over here, in the traditional service-oriented architecture world, we have violated that bounded context idea. Because if this service needs to do data transformations or other things like that, we've now smeared that responsibility out over our integration architecture. We now no longer have this encapsulated bounded context thing anymore. Now, if we want to make a change to one of these services, that's probably going to entail a change here. Of course, changes here ripple out to other places. Now it's very hard in the architecture to make a single change in one domain service and have that not ripple and change other things because they're all sharing all these same shared resources. Because everything is isolated in this bounded context, you don't have to worry about that. A couple of other side effects of this, though, if you have an enterprise service bus, it will accrue a pack of enterprise architects just like barnacles grow in the bottom of a ship in the ocean. Conway's law pretty much guarantees that this is going to happen, and when you're in this situation, there will come a day when one of these service teams really wants to put something on the enterprise service bus, and this pack of enterprise architects will tell them no for reasons, whatever those are, and now they've become a political force in your organization, not just some part of your architecture. I've seen it happen a lot. That's a side effect of Conway's law. But this sounds really dangerous, this choreography thing I've got set up over here. Because one of the things I'm trying to support in this architecture is say, you know, any one of these services can evolve at any rate that makes sense to them. In fact, that's one of the things we're really trying to do here, this observation that every part of your business doesn't grow at the same rate. Some parts of your business grow really fast, and some are really static and hardly change at all. We're trying to model that in architecture and say, we're going to let these services evolve at whatever rate makes most sense for them. But now this is kind of scary because now I'm integrating with this guy, and he's free to evolve and change in any way that he wants. How am I not going to wreck the world all the time by doing this? Well, the way that we solve that in this world are engineering practices. And the common engineering practice that's used here is this idea of a consumer-driven contract. So let me talk about consumer-driven contracts. This is an engineering practice that comes from the continuous delivery world. The idea here is, let's say that the team on the left is the service provider, and he is providing services for these three teams on the right. What's going to happen is when this team gets together with this team is going to come up with a set of unit and integration tests that defines what they need from this other team, and they're going to hand that set of tests to them. This team now promises, I will run those tests and keep them green every time I do a build of my code base. That's the idea of consumer-driven contracts. The consumers pass a contract up to the provider saying, this is what I need from you. As long as you don't break that, then we're cool. That means that this provider can evolve in any way that it wants to, as long as it doesn't break one of the contracts and everything's good. Of course, this takes the discipline to make sure that your teams run tests reliably for every time they do builds and honor tests and things like that. So there's some engineering discipline here, but once you have that discipline in place, now you can build services that evolve independently of one another without worrying about breaking integration points between those services. If you, in fact, there comes a day when one of these needs to evolve to break that contract, that's a placeholder for conversation between those two teams to get together again, reconcile whatever that breakage is going to be, and create a new set of contracts that they'll both honor on both ends. So this is what I meant earlier when I said one of the challenges in when doing things like coupling here is engineering practices. This is a good example of one of those engineering practices that allows you to do something and not worry about that you're going to break something. So in this world, we tend to like smart endpoints and dumb pipes, as decoupled and cohesive as possible, inspired by the way Unix pipes and filters work. Typically, the transport in this world is HTTP when we can get by with it because it's nice and easy to see what it is, it's easy to debug, or messaging over a lightweight bus if we need to go to some sort of binary format. Now, notice I was saying bad things about enterprise service buses earlier. Actually, if you have an enterprise service bus and you're just using it as a dumb pipe, we're okay with it. The thing we don't like about the enterprise service bus pattern is this idea of taking some of the things that should be in the bounded context and putting them somewhere else in your architecture, because now you've violated that bounded context idea. If you're just using it for plumbing, then we're okay with it. It's just a really expensive, fancy message queue. Here's another one of those prefer things. In this world, we tend to prefer REST over SOAP. SOAP, of course, is at its heart an RPC mechanism, which means it does parameter binding when you do integration points. And, of course, if the parameters don't line up exactly, even if they've evolved or something like that, then the magic just doesn't work. REST is more resource-oriented, which means that evolution doesn't necessarily break things. So if I have a RESTful resource that's about airplanes, and I have a resource that tells me things about seats, when they add engines and wings and other stuff to that resource, it doesn't invalidate my original query about seats if I just care about seats. And it's also a little more flexible in terms of endpoints, and so REST is a little more malleable at integration points, and that's a useful thing to have in our integration architecture. This doesn't mean you can't be successful with SOAP, but REST just seems to model this a little more friendlier and from an architectural standpoint. Another piece of advice from this microservices world is to standardize on integration, not on platform, and embrace polyglot solutions where it makes sense to do so. One of the big anti-patterns that companies get themselves involved in is trying to pick the one true platform, one true language to rule them all. And there isn't one. We just know that there's not. There are some solutions that are better right-sized with smaller language stacks. And so in this world, what we try to do is standardize on integration and then free up what people want to do on individual service teams. Now, we're not suggesting that this is just now the Wild West now where every team gets to pick their entire technology stack, but we made the observation, if you look at the spectrum for most companies that have on too few languages and platforms versus too many, most companies fall firmly on the too few side of this, not on the too many side of this, because they're trying to achieve, the one true vision of language. And so in this world, we'll embrace polyglot things. My colleague Sam Newman has written a really great book at O'Reilly about microservices, and I'll give you some of his advice. And one of his pieces of advice is standardize in the gaps between services and be flexible about what happens inside the boxes. So from an architectural level, pick, for example, REST level 2 or level 3 and say, okay, everybody adheres to that, then we don't really care what you implement that behavior in. Have 1, 2, or maybe 3 ways of integrating, but not 20 ways of integrating. And pick some sensible conventions and stick with them from an architectural standpoint. This is part of the enterprise or integration architect work in a microservices world, is making sure that the services can talk to one another in a reasonable way. Another side effect of the microservices world is decentralized data management. In the monolithic world, we tend to have monolithic architectures and we tend to have monolithic databases. There's an interesting side effect to this, because when you're doing shared resources for things like databases, what you end up doing is picking the database that will solve every single problem that you're going to encounter, because they all have to share the same monolithic database, which means that there's a 10% edge case that really needs all the industrial strength that every single project pays the price for. Because most of your data usage within your company doesn't need the industrial strength of a major database server, but you end up using it because, hey, we've got it, and everybody's using it for everything, and so we might as well just use it. So you end up buying extra complexity that you don't actually need. In this microservices world, we're really into this bounded context idea, which means that each one of these microservices, if they have persistence, will typically own their own persistence mechanism. Which means that on this service team, there's a DBA who manages this data persistence, whatever it happens to be. There's an operations person who makes sure that data gets backed up in the corporate standard way that data gets backed up and is on a regular backup and all that sort of stuff. So we don't throw away any of the kind of corporate hygiene that you have to have around things like data and backup and operations, et cetera. But the ownership just changes now because the person on this team is the one who owns that entirely. As I mentioned before, this tends to be a base versus an acid kind of world because base is a lot easier here. And this is Sam's advice: avoid distributed transactions if at all possible. It's not the transactions that are so bad, it's the distributed rollbacks that will keep you up at night. It's trying to get those to work correctly. Now, notice that we're really trying hard to get away from transactions as much as possible here, but we realize that in the real world you end up in some transactional situations sometimes. And so notice that in this case, it is not considered an absolute war crime if you do have two services that end up sharing the same database because they have a transactional context or something like that. This is one of those knowing compromises that you go in where pragmatism ends up winning up over architectural purity. For example, in relational databases, there are 7 normal forms that you can go in for your data? How many of you have your databases all the way to 7th normal form for your relational database? Come on, you can raise your hands, it's okay. No, you get to about 3rd normal form, you say, you know what, that's good enough, because now it's starting to get a little bit annoying. It's kind of the same thing here. We have this idea of architectural purity, but we're not going to build a rocket ship to the moon just to avoid doing something like this, so we'll try to be pragmatic here. And very often what's happening here, because you're not starting a greenfield project, you're decomposing a monolith into more of a services-based kind of world. I talked about structural coupling earlier, but temporal coupling may be the more important thing for you right now. It's the transactional coupling that exists inside your monolith, because that's a much easier thing to snip along those lines initially, so you don't have to worry about breaking those transactional contexts until later. And so that may, in fact, be one of the ways that determines how you slice up your existing monolith. But there are all sorts of interesting side effects of this kind of decentralized governance. Because let's say that you're on this services team, or this little customer service here, and you've made the observation, it's like, we're never going to have more than about 2,000 customers. We never have to do any kind of crazy querying or anything like that. And a member of this team is responsible for spinning up this database. Every time we do a build, we have to construct a machine and spin up a database instance and make sure all the data is on it and all that stuff. I've observed that, using tools like Puppet or Chef, you can go from a raw IP address to a running version of Mongo in about 90 seconds. And I'm pretty sure you cannot get the first Oracle install dialog to come up in just 90 seconds. And so this team may say, you know what, we don't need Oracle. We'd much rather pick Mongo or MySQL or something like that, and we'll just use a much simpler persistence mechanism, because now you're not shoving that choice down every team's neck to use something that's way over the capacity and therefore over the complexity of what they actually need. And maybe in 6 months they realize that, this is a terrible choice. It's not doing what we need to do. We need to rip that out and replace it with MySQL or Postgres or something like that. And nobody else cares, because none of the other services even knew what they were using for their persistence. And so they don't care at all, which means you don't get the ripple effect through your architecture when change happens. And this is actually really nice from a governance standpoint, because when you have monolithic architectures, when you make decisions about things, you affect everybody in that architecture. So if I need to decide, for example, on object relational mapping, everybody in that entire application server needs to share that, and so I've got to decide what's going to fit best for everybody. And of course, when it comes time to upgrade that, I've got to make sure everybody's ready to upgrade it, because they all share that resource. So that makes things like upgrades hard, so you put them off. That encourages you to do more and more big bang kind of stuff, which causes more pain. In the microservice world, when you let each team pick their own technology stack, governance becomes much easier now. Again, we're not saying let this become the wild, wild west, but pick a few sensible technology stacks and let teams implement those. And what you end up doing is it's taking a significantly less complexity burden because you're not using tools that are way overpowered for the problem you're trying to solve. You end up using way overpowered tools now because everybody shares the same tools, and so you end up getting stuck with them a lot. This world plays really nicely in infrastructure automation, things like deployment pipelines. I talk about that tomorrow when I talk about continuous delivery for architects. But that's actually a common pattern here is this works nicely in deployment pipelines, its ability to spin things up. And I'll talk about things like Docker, et cetera, on Friday. These microservices tend to be small, single responsibility. So you hear things like small enough to fit inside your head, small enough so it doesn't go past one screen on your editor. I've heard that metric. So small, in fact, that if you have a change you need to make to a microservice, rather than look at the existing one and try to understand what it does so you can make a change to it, if you know what the new version needs to do, just throw the old one away and rewrite the new one. It's only going to be 20 or 30 lines of code anyway. It's a microservice. It's a little tiny thing. And so the idea here is that they're so simple that rather than try to maintain one of them, you just throw it away and write the thing that you know it needs to do rather than try to retrofit something else that already does that. You'll also hear people say things like 100 to 1,000 lines of code-ish per service. That is and has always been a terrible metric for anything in code. So really it's the single responsibility thing I think is the key. Question?
Yeah, no, I'm interested in this sort of rewrite over maintainability when you say easier just to throw the old one away. Mm-hmm. But when everything is encapsulated inside that, when you have the data as well, mm-hmm. and if the data is going to have a slightly different shape, obviously the data is going to change, what do you then do about maintaining the history of everything that happened before?
So you're going to be a product team that builds a service, which means you have a DBA as part of your product team. They're going to figure out what the data needs to happen between the old version of the service and the new version of the service. So as the coders are writing the new version of the service, the data people are doing whatever transformation needs to happen to get it in the format that you need for the new service. Because you're all on the same team, you all know exactly the day that this needs to happen, so you all work on the exact same problem at the exact same time.
Don't you just end up with a whole load of historical things that we don't use those tables anymore because that's version 1. But we're now on version 30, so we have like 29 more of these ones.
Well, no. You're very strongly encouraged to refactor away those tables. They're literally not used anymore. Get rid of them. Why are they there? But you can migrate that data and so that you keep using that data. So that you're going to have a DBA on the service that will keep migrating that stuff into the format that you need it. It's a very tightly encapsulated team. That's the idea, is that somebody on the team handles that. So let's talk about decomposing a monolith. So like I said, a lot of people are not building a greenfield microservice environment, which would be nice. What you're doing instead is taking an existing monolithic architecture and trying to break it down into more of a services-based architecture. And this is a good motivation, and you don't have to get all the way to microservices to be successful here. When you start thinking about decomposing it, there are several different boundaries you can think about as ways to decompose things. I've already talked about structural boundaries, things like afferent-effort coupling, and look at the coupling characteristics of code base and decide how to pull them apart. But you may also look at transactional boundaries. This is if you have a really transactional monolithic system, think about what if the first thing I did was just honor the transactions that are already there and shave those things off as services. Very often those map pretty nicely to your domain concepts in your world because a transaction encapsulates the context of a domain. And so that may be an easier way to start decomposing. So you take a monolith and you break it down into 4 or 5 services that preserve transactions and then take those and break those down into smaller pieces and smaller pieces. And that's this idea of decomposing things like that. Or maybe you end up going the full inverse Conway maneuver and do it by domain, build domain-specific teams and start decomposing things that way. That's actually easier from a greenfield perspective, but it is possible if you're refactoring. Or maybe you have organizational constraints like geography or location or something like that, and you want to build things based on geography. Maybe that's how you partition things. There was a famous, this is probably 30 years ago, famous architect, I think it was Jerry Weinberg, who somebody asked him, was like, how many parts is this architecture going to have? And he said, well, I know it's going to have 7 parts. I don't know what those 7 parts are going to be, but I have 7 teams in 7 locations, so I know it's going to be in 7 parts. So that's really the Conway's law reifying itself, that realizing that, hey, if we got 7 geographically dispersed teams, we're going to have 7 parts of the architecture. You should design it to have 7 parts and build communication structures that assume 7 parts. That's splitting things up along organizational boundaries. So if you're looking at doing things structurally, this is that picture I showed you before from X-ray of this horrible monolith. But like I said, if you look at, there are definite hotspots here of things that are going on. There's an architectural anti-pattern known as a God object, something that knows too much or does too much. And very frequently, these hotspots like this are going to represent God objects. Now, I happen to know what this code base does, and a lot of the coupling points up here of how these things are coupled together across like this have to do with like client, customer address, and that sort of information, and kind of historical information like that. And so looking at this just from the structural standpoint, you can kind of say, well, if I do a cut across here, I cut the fewest number of lines. And so that's part of the motivation here of looking at it structurally. This is not like a really precise analytical tool. This is very, very coarse grain and very kind of experiment or very speculative. But this does give you a way to look at things. When you're thinking about structural decomposition, think about how many things am I going to have to break, how many lines am I going to have to snip, and how difficult is that going to be. So I've been talking about a bunch of characteristics and how things are more complicated in this world. Let's talk about some benefits that you get from this style of architecture. One of them is really interesting asynchronous behavior. So let's say that you've got a bunch of microservices running around, and you're trying to build a page. So let's say you're someone like Amazon. You're a commercial site and using microservices to build a page. And so a user comes in and makes a request. The website is going to send off a request, a whole bunch of microservices, a bunch of services, and then start a clock. Clock's important because you can bet that Amazon knows the exact number that balances the amount of information they can get on their page versus taking so long to draw that people start wandering away and get bored and won't wait for it. I don't know what that number is, but you can bet they know exactly what that number is. So they have a strict SLA for these services. You've got to get stuff back to me in time for me to render the page within the time for this clock to go off. And so some of these services will start sending stuff back, and they will get aggregated and getting ready for display. And then eventually the clock's going to expire. Time is up, we need to render a page, and the page gets rendered. Now some of these services may still send responses back, but you know what, you're too late. Maybe next time you'll get back fast enough to actually get on the page, but you didn't make it this time because we had this strict SLA. And so in this world, timely partial results are preferred over slow complete results. Because we're trying to meet an SLA, we're trying to build stuff. So in the Amazon case, maybe when you make this request, the first thing it does is go off and say, okay, we want to put the New York Times bestseller list on the home page. Send out 2 service calls, one to get the cached list and one to get the real one. The cached one comes back right away, and so the aggregator grabs that and holds on to it, and it's waiting for the real list to come back, and it doesn't come back within the SLA, so they get the cached version. If they really want to go see the New York Times bestseller, they'll click on that and they'll take the time to synchronously get that information. But if we're just trying to draw the page, we're not going to delay drawing the page just so we get more complete information that your user may not actually want, and they'd rather have a faster load time. The other side effect of this is in this world, return is mostly data structures, mostly things like JSON, and this aggregates and figures out how to use those to draw a page. So we're not sending UI stuff back from these. These tends to be data structures, and the UI is handled by the front end or something on the front end who ranks and aggregates those returns for display. Another good example of this kind of broad asynchronicity is the way that Google handles this semi-magical, did you really mean this? You know how they do that? So the way that works at Google is when you make a search request at Google, it doesn't do a single search request. It does a few hundred. It takes your search string and permutates it in common misspelling ways like transposing letters and swapping out vowels and things like that. If they get a search result back that has really high correlation and everything else has really low, they'll say, did you really mean this? Because I got really good search results back for this and almost nothing for the trash you typed in. So I think you probably meant this. Now think about how fast that Google search comes back. That's hundreds of service calls per user. How many users are they handling per second in their infrastructure? That is a kind of scale that's hard to achieve otherwise, but they're doing this because they've done this from an operational standpoint and use that to scale all these services out. Here's another example of a common architectural pattern in this world. So when you have a traditional monolith, you tend to have a user interface, you tend to have some sort of object relational mapping thing in here, and you have a relational database that it maps to. One of the really cool things that the Clojure community has given us is resurrected an archaic term called complect, C-O-M-P-L-E-C-T. To complect two things together is to braid or weave them together, and very often problems in software is because we have inadvertently complected things together. And here's an example. When you do updates and reads from the same mechanism, you have complected updates and reads together, and it's complicated. One of the things that is very common in the microservices world is this pattern called CQRS that Greg Young came up with, the command query responsibility segregation, that says rather than have a single data store, you have two. Updates come through the command model and end up in this relational database, and they trickle upward into this update database, and all queries come from that database. Notice this is very much an eventual consistency kind of world, but these two things are much simpler in this world because they never have to worry about contentions about updates or locks or anything like that, because this is purely update and the other is purely read. This is also how you handle things like reporting, typically in a microservices kind of world, because once you've got something like this set up, it's not at all uncommon to create a kind of event streaming kind of architecture, where this updates not only the kind of system of record data, but also maybe pre-updates a denormalized reporting database, and all your reporting services run off this guy. Again, we're in an eventual consistency kind of world here, so we're not looking for the sole source of truth, we're looking for eventual consistency. And maybe this is a regular update database, and this is a denormalized data warehouse for reporting purposes. And maybe you've got another database over here that's a graph database because you're doing some sort of graph stuff that makes more sense for that shape data. You can have actually a bunch of things here and wire services to them appropriately. Okay, so that's characteristics. Let's talk about some engineering practices, some practicalities. One of the characteristics in this world is that clients must respond gracefully to provider failure. The secret to building the most fragile architecture on earth is make everything synchronous. It'll fall over like that. So we want asynchronicity here. So it's very common to build a mechanism in each service that has an asynchronous message queue inside the service, so requests come into it can stack up. And notice that from an operational standpoint, you can notice that and spin up more versions of that service and start balancing across it in real time and respond to changes like that in real time if each one of them has the ability to withstand a little bit of a storm of too many requests, enough time to scale up more services to handle it. We also do really aggressive monitoring in this world. We do several different kinds of monitoring, business relevant monitoring, looking at sales and other things like that. Architectural monitoring, I'll talk more about that in just a second, about integration and disintegration. And also semantic monitoring, doing things like running endpoint tests. We have cucumber tests. Anytime we have to version endpoint, we have cucumber tests that model both sides of that, and we frequently run those against a production infrastructure as well. The theory being, well, we made this assumption at development time. We want to make sure that still the same assumption is true at production time. And if you build your production ecosystem so that you can run things like tests against it, it's just another consumer of those services. As I mentioned, monitoring is a big deal in this world. Monitoring a monolith is hard enough, but monitoring a whole bunch of microservices is way, way harder because you've got lots and lots of these things running around. And so part of the advice here is you have to get much better at monitoring in this world. I don't know what the exact number is, but Netflix generates some sort of staggering, better than 10,000 messages a second in their ecosystem. You have to have good ways of aggregating and learning from that flood of data. A lot of DevOps people think that the ultimate in sophistication is using an SSH multiplexer so you can see what's happening on a bunch of machines at a time, but this does not scale when you get to the level of microservices kind of world. So Sam says, don't bother doing this. What you need instead are tools that handle this job for you. There are a bunch of tools out there like Logstash and Kibana that will handle huge volumes of logs, aggregate those things together, and give you realistic data about what's happening in your ecosystem. So for example, a very common thing here is to do aggregating monitors so that you can look at individual service response times, but also aggregate response times together so you can get a rolled up picture. because you're going to want to know at some point, hey, I'm making a customer request into this microservice ecosystem, and it's going to bounce around to a bunch of services and then come out with some result at the end. I'd like to know what each of them are doing, but I'd like to know the cumulative result as well. And that's this idea of aggregating monitors together. And a lot of these tools will let you do that, look at individual response times, but then also roll up and tell you how many requests were serviced, et cetera, for a particular business case. This is Sam's advice, is capture metrics and logs for each node and aggregate them to get a rolled up picture. Before I go on here, let me point you to a resource before I forget to do it, because it would be a terrible thing if I forget to do this. I'll actually point this to you in the workshop on Friday, but I'll point it for you guys who are not coming there. There's a site called DevOpsBookmarks.com that is your new best friend. DevOpsBookmarks.com. This is a Roku site that was set up by a bunch of my colleagues in India. And what they're doing is there is an absolute flood of tools in the DevOps space, and it changes and grows every day. And so what they did was create this live site called DevOps Bookmarks, trying to keep track of all these things. So if you need log aggregators, you go to DevOpsBookmarks.com, click on log aggregators on the left-hand side, and pick which platform you're on, Windows, Linux, whatever, and it will show you all the open source log aggregators that exist out there. So provisioning and service discovery and all these things that I'm talking about here, there are categories for tools, all open source, that do these things, including things like log aggregators. Another common practice in this world is do synthetic transactions. Once you set up a really complex business system that does microservice stuff, you want to make sure that things like sales work correctly. And so a really common thing to do in this world is to wire your transactions with basically a flag that says this is a synthetic transaction. So when you get to the very end of the business process, don't commit it to the database or whatever that does to make it an irrevocable actual transaction, so that you can track it as if it were a real thing through your production ecosystem. When you make it like this so that it's exactly like production except for the flag, then it gives you really realistic ways of monitoring to see what realistic business transactions look like. So this is Sam's advice: use synthetic transactions to test production systems. That's actually a piece of advice from this book, and pretty much everything in this book you need to ace before you start one of these kind of architectures. I'll talk about circuit breakers and other stuff in a second, but all these patterns in release that really define a bunch of these engineering practices in DevOps, including things like synthetic transactions, which are the entry path to this kind of architecture. Make sure, if you set up synthetic transactions, that you remember to flip the flag. There's a famous case study where 200 washing machines showed up at the home office of the headquarters. It's like, oh no, we didn't actually want 200 washing machines. We just forgot to flip the flag. So if you would put those back on the truck, please, and take them back to the warehouse, that would be nice. Another common thing in this world of correlation IDs, this allows you to track through, because it's not at all uncommon in one of these microservice environments where you'll have a dozen different services are handling the same kind of request, and they're being managed by a load balancer, some sort of service discovery tool. Correlation IDs let you track and find out what happened, which exact instances of services you went through, in case you're trying to debug something unusual that's going on. This is another one of those best practices there. Use correlation IDs to track down nasty bugs for interactions that you can't quite put your finger on. This allows you to find out exactly what path it took through the topology of your architecture. So I've said something that may be bothering you, because I've said several times behaviors that I want all my services to implement. But how can I ensure that? So I want every one of my services to be able to queue input requests for that service. But I don't have to write that for every service, because I'd mess it up at some point. I also want them all to react the exact same way to logs and monitoring and metrics that I'm gathering. So I want to ensure consistency across these things. And so there are tools out there, these service template tools, that let you take the service behavior for what it is, but then there's an integration piece, because I need to be able to integrate with the rest of the ecosystem. I need to be able to interact with downstream processes. I need to be able to interact with metrics and other things like that. These are tools like Drop Wizard or Spring Boot. These are service templates. This is a special category. The idea is you create a consistent template for all your services. It encapsulates the behavior you want every service to exhibit, the operational behavior, whatever kind of integration architecture stuff you want to bake into it. And now for each team, all you do is write the behavior in here, the 100 or 1,000 lines of code, and not worry about all that plumbing stuff, because the plumbing's already been done for you. That's this idea of a service template, and there are a handful of these tools out there. Again, DevOps Bookmarks has a whole list of the service template tools to do this. The two most popular ones are probably Drop Wizard and Spring Boot, but that's exactly what these are designed to do. As far as version control repositories, this is one of those prefer things. You have two options here. You could either use one repository for all your services, or you could have repository per service. We slightly prefer having a repository as a service rather than a monolithic repository, because when you have a monolithic repository, the temptation is still there to couple things from a code standpoint because you've got all the code there. If you have a separate repository for every one of them, this forces you to integrate via a continuous integration pipeline, which forces to make sure that you never cheated and relied on something that you should not have. So let's talk for a second about testing microservices. This is a really tricky engineering challenge because each of these microservices may have a significant number of moving parts. So here is a representative microservice that has all the moving parts that one of these guys may have. It has things like the domain logic, which is the actual logic that's part of this microservice. This service layer, things provided by the service template for caching and all that sort of stuff. It has ways of interacting with external services via a gateway or some sort of lookup mechanism. It may have data repositories, internal, and then data mappers and ORM. It may have its own data store that's inside its bounded context, or it may interact with an external data store. So let's talk about the different levels of testing. So in the continuous delivery, where we'll talk about several levels of testing, let's talk about what those levels of testing look like here. The first of these is unit testing. And we have two different kinds of unit testing that we want to do here. The first one is sociable unit testing. This focuses on testing the behavior of modules by observing changes in state, which is essentially black box testing. So in this case, you're instantiating real things and having them interact with real objects. And so you want sociable testing for your domain objects because you want them to be as realistic as possible. You don't want them to talk to fake, stubbed or mocked or anything. You want them to represent real kind of business cases because that's really important stuff. The other kind of unit tests that you see are solitary, but you can't even see. It's a pink box right here. You can barely see it right there. But all these that have a pink box on them are solitary. These are the tests that looks at interaction collaborations between object and dependencies, but are using test doubles and stubs. And so, for example, you may have solitary unit testing to make sure that your repository maps correctly to ORM. You may have stubs out here to make sure that gateways and other things like that work, but you don't really worry about the contents of those, really more doing structural testing. For integration testing, one of the things that you do here is to do gateway integration test that allows you to track things like protocol errors and things like that can happen in the interaction with the rest of the world. So basically you're making sure that it interacts correctly with the rest of the world. That's one form of integration testing. If you have something like an external data store or want to do integration testing within your microservice, then this is another place where you may do integration testing to test that things like ORMs have the right schema and they're all matched up, and et cetera. When you do component testing, you have a couple of different options here. One version of component testing basically says wire the microservice so that it has a testing flag and instantiate in-memory data and those sorts of things so that you can boot it up and let it test itself, basically make it self-testing. This leads to faster text execution times and minimizes the number of moving parts because it's completely self-contained, but it also means that the artifact being tested has to be more complicated because it has to know that when it detects that it's in test mode, it needs to start up with an in-memory data store versus an external data store and to stub external requests and things like that. This is easier if you're doing completely self-contained tests. The other way of doing this, some tools that allow you to do this that generate shims for you automatically if you want to mock out all these kind of interactions. Nproc Tester and Plasma are both tools that allow you to do this level of component testing. We're given some service, and given what it's expecting, it'll automatically mock those endpoints and things for you. The other variation of component testing is actually drive the entire thing, create a stub service that drives it in a realistic way. All the intelligence has to be here about what it sends in and gets back to make sure that it's okay. But the advantage here is you don't have to change anything inside the service. It's just reacting as it would in its normal ecosystem. All the complexity now is in this test harness rather than scattered through here in some sort of testing flag. I mentioned consumer during contracts earlier as a testing technique, and this is the contract testing in microservices. This is the common pattern for doing consumer during contracts. And here are open source tools that allow you to do consumer during contracts. This one's in heavy use in Australia, and this is being used in Brazil. Both of these were created as part of ThoughtWorks projects, and both of them implemented a consumer-driven contracts open source framework without realizing the other team was doing it, and they ended up naming them almost the same thing, Pact and Pacto, but they're both in active development right now, so is Janus. These are really nice tools for setting up these contract tests. And then finally, for end-to-end tests on a microservice, you want as few of these as possible because it's a complex thing to set up. You want to focus on personas and user journeys. Don't try to test every possible scenario. So you're really after kind of happy pass and well-known exception pass here. Choose the things that you're trying to test wisely. Try not to do comprehensive end-to-end tests because that requires bootstrapping a large bit of infrastructure to do that. Rely on infrastructure for code for repeatability, whether that's using Puppet or Chef or using something like Docker containers or something like AWS. And then try to make tests as data independent as possible so you don't have to worry about things like data dependencies. So this is the testing pyramid for microservices. This testing pyramid is a well-known artifact out in the world. The water guys have an example of this. But this shows you the relative number of the kinds of tests that you'll have and kind of the complexity level as you ascend that stack. All right, finally, let's talk now about deploying these guys. One of the anti-patterns in this world is to have to understand how to deploy a bunch of different things. You don't want to have your operations to have to know how to deploy some Java stuff and some Ruby stuff and some Google Go stuff, et cetera. What you want to do is drive consistency here, and the typical thing here is to create a single deployment mechanism and deploy everything on top of that. This is where things like Docker comes in really handy because you can say my deployment unit is Docker, and now everything can just fit inside a Docker container. The goal here is to abstract out the underlying platform differences so that you have a uniform deployment mechanism. So for example, a common thing to do in the Java world, if you have a whole bunch of Java little microservices, is to build each one of them so that they have a main method in them and they can self-host themselves, so they embed Jetty or Simple Web or something like that inside them, so that you can have a whole directory of these little jar files and say for each jar file, tell them to execute themselves and they can all bootstrap themselves. That's this idea of having a consistent way of bootstrapping everything and not have this magic formula that you have to follow for different kinds of things. Another piece of good advice here is don't let changes build up. The temptation always when you've got independent teams building things is to put things in a staging environment and then say, well, but these guys are almost done, so let's test them, and then, these guys are almost done, and things start building up. You're much better off doing a continuous deployment kind of model with these guys. Try to get these things out live in the ecosystem as quickly as possible. This is Sam's advice. Don't let changes build up. Release as soon as you can, preferably one at a time. But this may trigger your spidey sense system of, this is too scary. We're in continuous deployment now. We're afraid we're going to break something if we put things live one at a time as they happen. But there's a different perspective here that will save you from that I'll talk about in just a second. In fact, let's talk about it now, an integration and disintegration. So on Friday, I'm doing a continuous delivery workshop, and I'm going to talk about a bunch of engineering practices that are common in this microservices world. Here's one of them. So remember I talked about complecting earlier? One of the things that we have inadvertently complected together is that saying that deploying something and releasing it to the users is one thing. If you can separate those two things, you cut down on the risk of that. And so this is a common practice in this world that components are deployed into a production ecosystem. But that doesn't mean that the feature inside that component is turned on yet, because a common practice in this world are use things like feature toggles or feature flags or branch by abstraction, so that you put this into the production ecosystem and monitor it to make sure everything's cool, hasn't broken anything. And then features are released by telling that component, okay, turn your feature on now. This means that you can have a bunch of different services running. Some of them may be almost the same thing. This is a really common to play A/B testing and what-if games. Maybe this is a new search algorithm that I want to try out for 1% of my users or something like that. We still haven't impacted the users yet because in this kind of world, applications consist of routing. And so in this world, you deploy something into the ecosystem and monitor. You turn those features on and monitor, and then you route to them, and if they start misbehaving somehow, you don't have to roll back your whole architecture. You just route back away from that offending service back to the one it was using before, and then figure out how to fix it and maybe route back to it. And over time, you evolve these services so they add more and more capabilities, and people route to them, and other ones get left behind over time, so it's a very Darwinistic kind of environment. One of the practices we talk about in continuous delivery is this idea of blue-green deployments, where you have two different slices of your stack, a blue slice and a green slice, and the idea is you can move between those two. In the services-based world, we basically have blue-green at the service level. You deploy something, you release it, you route to it. If something messes up, you reroute away from it. But now you can do all sorts of what-if games and play canary releasing a small number of new features to users and monitor to make sure things work. All these things are supported in this kind of architecture. And so toward this question of how big again, notice that if you have the right engineering practices in place, which may be a big if, but if you have the right engineering practices in place, the higher the number of services you have, you drive the risk of release down. Because when you're deploying a monolith, Big Bang style at 3 a.m. on a Saturday morning, it's all risk. There's nothing that mitigates the just pure risk of that. But if you have lots of services, that means they're smaller and smaller and smaller, and so you're displacing less and less of the production ecosystem when you put one of these out, and you actually incur less risk in this world than in a monolithic kind of world. I mentioned before that we monitor in this world. We monitor the services, of course, but we also monitor the routes, and this is part of the perspective that Netflix gave us, was that, so the idea here is that I've got a service running, let's say we're Netflix, and I have a star rating service running. And somebody comes out with a star rating service that supports half-star ratings. And everybody at Netflix that rates stuff says, ooh, I like the half-star rating. And so they start migrating over to that service, and it starts getting more traffic until the original service rating, no one's routing to that anymore. They have a garbage collection run in their architecture at Netflix that goes and looks for services that are running but that no one ever routes to them anymore and disintegrates them out of their architecture. So they don't just leave services running forever. If no one's using that service, it gets slurped out of the architecture to get replaced by something else. So they look at real usage to determine should something be around or not. Another example from the Release It book is a circuit breaker. The idea of a circuit breaker is when you have a call for something, have a status before you make that call. Before you make a synchronous call to something, call a status to make sure it's alive. And if it's not, don't make that call. This is the idea of a circuit breaker. And again, are a bunch of these engineering practices from Release It, timeout, circuit breakers, and bulkheads to allow you to avoid cascading failures in this kind of environment. So let's summarize this stuff. As I've said a couple of times before now, you need to be this tall before you really start down this path. These kind of architectures are much more complex than monolithic architectures, significantly more complex, and it takes a lot of engineering discipline to make these things work. Because now you're relying on things like consumer-driven contracts, you're relying on every single development team running all their tests every time they do a build and making sure those things stay green and they don't get slack about that. And so it takes a fair amount of discipline to do this. And so a lot of these engineering practices are things that are kind of prerequisites to make this work. These are much more complex than traditional architectures, but they give you some unique benefits. The way that you can operate at scale here is kind of unprecedented. You look at the way Netflix works, for example, the way that Amazon works. Those are companies that are operating at extreme scale by leveraging this kind of architectural pattern. But this is definitely not the solution for every problem. It is if you're in an organization that's trying to build change as a first-class citizen. That's really the main benefit we're promoting here. I mentioned the inverse cowboy maneuver. Build teams that look like the architecture you want, and it will follow. I also mentioned efferent coupling as a metric. And when I talked about it purely as a code metric. I didn't mention, by the way, in the .NET space, Independ is a good tool to give you efferent coupling for your code base. But I also suggest you have low efferent coupling for your team as well. You don't want every team to understand what every other team is doing in your ecosystem, because there's a lot of it's just stuff they don't need to know, and it's a lot more burden than they need. And so what you really want are teams that understand some of what the teams that they're integrating with, they understand some of what they're doing, and a lot of this other stuff they don't have to know about, but we really don't want to burden everybody with knowing everything in this world. This is why that inverse Conway maneuver works really well. Split people up into domain-centric teams, and now they become subject matter experts in their domain, and they don't have to understand a lot of the other domains except what they need to do to be able to integrate with them. And so when you take all these engineering practices together, plus this style of architecture together, the goal here, from an engineering practice standpoint, is this. Teams with low effort coupling deliver relatively independently into a common integration pipeline without breaking each other's builds. There's a common integration pipeline that's in gray here that you can't see at all. It's right here, where all these services are actually being deployed to. But all these teams have low effort coupling. They have consumer-driven contracts between them to make sure that they're not breaking things, so that each service is allowed to evolve at a rate that's reasonable for that service. Not every team has to understand what every other team is doing, but the teams that they do need to integrate with, they have things like consumer-driven contracts in place to make sure that they don't actually break stuff when they do integration with them. So that's all the material I have. Any questions left over about this? I'm guessing there are probably a few. So I've been rolling along a straight track. Yes?
So I'll start. So one of the old tricks of software development is a nightmare for programmers is having a method with 10,000 lines.
Mm-hmm.
The next programmer says project with 10,000 methods.
Mm-hmm.
Now we have a problem with 10,000 classes.
Mm-hmm.
You're suggesting we can have a problem with 10,000 services.
Could be.
Except the problem is you don't have any tools in there that is accurate between services.
Oh, sure you do. Netflix has got a ton of them. Netflix has got, in fact, Adrian Crockford, who formerly of Netflix, just announced a tool last week, an open source tool called Spigo, S-P-I-G-O, that you point to an architecture like this and it graphs it and shows you all the effort coupling points. People are building tools to do this.
Well, it seems to me, I mean, I'm not against microservices.
Mm-hmm.
It seems to me like the whole idea of single responsibility rather than domain responsibility goes a bit too far out into the coupling domain versus the cohesion domain of what services do.
Okay, then you should do services, not microservices. Problem solved.
Already,
So you don't have to go to microservices. This is a very specialized architecture for very specialized kind of things. The point, though, is that if you do have pretty much every method as a service and it's operationalized as a service, it's really easy to make changes in this world. So you look to the Lambda, the Amazon Lambda architecture, if you looked at this, they literally instantiate a platform for every single service call. 3 seconds is the longest call they will allow on the Lambda platform. So now they're getting it down to, you're not spinning up a new set of servers and all that stuff per website, it's per request. It spins up an ecosystem and then dumps it. So now you're talking about really fast change and really fast, really tiny little micro things. So this is the way the world is going, I think, from an operational standpoint. I hear your concerns, absolutely. So what this really does is make coupling a much bigger part of your life than it ever was before. That's what you find when you get into one of these architectures. All of a sudden, you think about coupling all the time. Whereas you kind of thought about it occasionally in a monolith, you think about it all the time now as to how that impacts your life. Other questions? Yes?
more of an experience one. So how big was the rule of thumb experience? When would you consider going down this route? It's like the rule of the pencil software and inherent cost and complexity software.
I don't think it's the size. I don't think the size is the determiner here. The question is, do I want to be able to make really incremental changes at an architectural level at any time I want? That's the thing that this is really trying to support, is that really fine-grained level of change that has no impact on the rest of the architecture. It's really the idea that we can let teams build new things and ease them into the ecosystem and then kind of Darwinistically evolve behavior. So I don't think it's a size thing at all. I think it's really more capabilities based. I want to support this specialized capability, which is making change really super easy. And a lot of people that will go down this path are going to do it because it's a shiny new thing, and they don't really need that level of change. And so you're better off at a services-based architecture that uses more kind of plumbing, like I'm not a huge fan of enterprise service buses, but, less kind of really this kind of almost fanatical level of encapsulation. Most services-based don't quite have that level, and that's good. That's perfectly fine for them. I've got probably time for one more question. So anybody want to do one last question? Nope, nobody wants to take the last question. All right, then I will set you free. Thanks very much for coming. Hope you enjoyed it. And thanks. You can manage the collaboration between these services. It forces a coarser grained coupling than you have if you have application architecture. You have to think more carefully about what kind of information is passed back and forth and things like aggregate and composite information, how you want to handle that. If you have really undisciplined coupling in a microservices architecture, you get a real mess. The classic anti-pattern here is you have a tool that lets you right-click and create web service, and boom, create 1,000 of them, and you've created an anti-pattern called a spider web architecture where you can't really figure out what's going on anymore. And now your coupling dynamics have become an integration issue, not just an application architecture issue. And so you have to think a lot more carefully about how things are coupled together in one of these worlds, because now this is a lot more of a first-class citizen in this kind of world. And we'll see that as we start talking about the characteristics of microservices directly. The next concept, definition kind of thing I want to talk about is ACID versus base. We've all been fat and happy using ACID transactions for a few decades now, and we all love those. And our business users, in fact, love them in an unnatural way. Love them too much, in fact, because most of the world's not really transactional. So we all know what ACID means: atomic, consistent, isolated, and durable. This is one of the magic superpowers of relational databases. They give you this thing pretty much for free. But more of this services and microservices world is much more of the base kind of world: basic availability, soft state, and eventual consistency, where you don't guarantee transactions across machines, but they will eventually become consistent with one another. One of the things that drives base over ACID is this observation that as you get a certain number of distribution for your data, as you get more and more users and more data, and you are inevitably required to distribute it more and more ways, you reach a certain point where you can no longer guarantee the ACID properties that you get from relational databases anymore. This is what's known as the CAP theorem. There's a mathematical proof here that once you reach a certain level of distribution, you can no longer prove ACID. And so that's why all big systems ultimately have to succumb to doing base and eventual consistency rather than doing ACID transactions, because once you hit a certain scale, you just literally can't do it anymore. But this is actually a good thing for us, because we've sold our users on this idea that transactions are just as free as the air and you can have all sorts of transactional behavior. All right, good afternoon, everyone. I'm going to get started. Welcome. As you probably guessed, this is Building Microservice Architectures. I just came back actually from a conference in Boston, the first O'Reilly Software Architecture Conference, and almost half the sessions there were about microservices in one way or another. This is insanely popular, and a lot of people are doing it, going headlong into it without fully understanding the pitfalls. And so I want to talk about, get to the root cause of why this is so insanely popular as I go along here today. So what I'm going to talk about here today, first I'm going to talk about some definitions. One of the tricky things anytime you talk about architecture is getting the right context in place to understand enough of what you're talking about to make sense of it. So I'll talk about some definitions that are pertinent in this microservice world, including some things like some code metrics that you can use as an architect to, as I suspect, many of you are in the situation of taking a monolithic application architecture and decomposing it into a services or microservices architecture. So I'll talk about some metrics and tools that allow you to do that. I also talk about the specific problem that microservices are trying to solve. This is not the end-all cure cancer, one-size architecture fits all problems kind of solution. There are very specific things it enables you to do, and it fixes a particular interesting problem that we've had a long time in architecture, and so I'll talk about what that is. Then I'll talk about some characteristics of microservice architectures, in particular in contrast to monolithic architectures, and then a bunch of engineering practices. It turns out that is one of the defining characteristics of microservice architectures, is you have to pay a lot of attention to the engineering practices around both development and operations unless you want to create a kind of a train wreck. So let's talk about some definitions. And the first one I want to talk about is a concept that comes to us from domain-driven design by Eric Evans. Domain-driven design is ostensibly an object modeling technique where you are supposed to take ideas and then decompose them into domains and then think about how domains communicate with one another. The implementation book over here by Vaughn Vernon is quite good in reifying these very abstract concepts into something closer to software concepts. But there's one idea in domain-driven design in particular that's quite important in this microservices world, and it's this idea in domain-driven design of start thinking about, okay, what's the least structural friction that I'll get as I start pulling this apart? In this combination, how many things will I have to break? And so it's a very coarse-grained kind of tool, but I'll show you how you can use this to kind of right-size your decomposition a little bit later on. These two metrics are really interesting to us because software architecture always represents the tension between coupling and cohesion. If you think about the first kinds of applications anybody built on mainframes where the data and the code and everything resided in one big memory space, that's all cohesion and no coupling. As soon as you start pulling things apart and making them communicate with one another, then you start talking about coupling as an interesting characteristic in software. And that is, in fact, one of the interesting things that microservices do to us from an architectural level, because microservices promote coupling from application to integration architecture. Here's what I mean by that. When you look at a monolithic application that consists of a whole bunch of classes that communicate with one another, you don't really think much about how they communicate with one another or how long it takes for them to communicate with one another for method calls. So you don't worry about, there's a method in here that makes a method call on this other class inside a loop and does it a couple of hundred times. It's no big deal. But when you take this monolith and decompose it into a set of services, now you have a much coarser grained kind of connection between those services. Now each of these services still has classes and methods and all that stuff inside it, but the way that they communicate with one another now is part of integration architecture, not application architecture. There's a famous document that I'll point you to. I don't have it on my slide, but I'll point you to, called Peter Deutsch's The Fallacies of Distributed Computing. This document's been around for about 20 years now, and it's all the mistaken assumptions people make when they start distributing things. The mistakes like that latency will be 0 and that all the machines will actually be up and available and running and ready to accept calls, and these are all mistakes people make. And this is another one of those mistakes people make that you've got to now start thinking about. What do those messages look like just being passed between these microservices, because now this is part of my integration architecture, no longer internal to my application architecture. And so you have to be really explicit about coupling here and think about how things are coupled together. One of the ways that we build protections into these kind of architectures are with specific engineering practices. I'll talk about consumer-driven contracts in a bit as to how bounded context. So one of the things that domain-driven design defines is that when you define a domain boundary, like customer, for example, it is its own bounded context, meaning that the things within the customer domain know all the intimate details of how things work, but nothing outside that customer domain knows any of those details. They can find out by doing some sort of messaging or something like that, but the internal details of how that thing works are completely encapsulated. Now, domain-driven design is a logical construct. It is a modeling tool. But what we're doing in the microservices world is reifying this concept of bounded context and putting it into practice. And so when you look at a microservice, it really does meet this bounded context idea, both logically and more importantly, physically. So when we create a microservice, it is completely encapsulated. So if it needs persistence, that's encapsulated inside the microservice. Everything that it needs in its life is encapsulated inside it, and it meets this bounded context idea. And it turns out that's one of the defining characteristics of microservices, and the reason why is that is what gives microservices their superpower. And I'll talk about their superpower in just a second. The next definition I want to talk about are some coupling metrics, structural coupling metrics in code. And two in particular that I want to point to here. For any code artifact that you have, this could be a package or a namespace or it could be a class, the afferent coupling to that class are the number of incoming connections or references to that class, and the efferent coupling is the number of outgoing connections. And the easy way to remember this, because these are very similar words, is that efferent coupling, the outgoing connection, starts with the same first letter as the English word exit, and so that's how you know those are the outgoing ones versus the incoming ones. This is an interesting metric for us to track because we care a lot about coupling metrics in this world. Particularly when you're starting to look at architectural characteristics of code, structural coupling is one of the interesting things that you want to look at from an architectural standpoint. And there are some tools out in the world that allow you to look at structural coupling in a variety of different ways. Some of these tools were inspired by very old school Smalltalk tools. There was a really cool tool in the Smalltalk world called Code Crawler, and X-Ray is an implementation of this in the Java world. This is a little tricky to see because this projector has stunningly bad contrast. But basically, this is a code base. The lines that you see here are inheritance lines. There are lines between these guys. The boxes represent classes. The length of the box indicates the number of lines in the class. The width of the box indicates the number of methods. But the interesting thing for us is that when you click on one of these guys, it will show you its afferent and efferent coupling. There are more lines here. You just can't see them very well. But the weight of the line here indicates the strength of the coupling between these two classes. And so what that suggests is if you wanted to pull these two classes apart, ones with really bold lines between them are going to be harder to pull apart because they have more coupling points between those two classes. The more useful view in X-Ray is this kind of pie chart view. And again, it's kind of hard to see because the contrast is shockingly bad in this projector. But there are actually a spider web of lines here. The only one you can really boldly see right here. But the point of this is, you can see this a little better, is that there are definite patterns in the way that these structures are coupled together, and you can use that patterning to start thinking about how to pull them apart. I'll show you one that's so dense you can't avoid seeing the lines on it here in just a second. This is a class dependency, and one of the problems you run into is the hairball effect, where you start getting too many lines overlaid on top of one another. And X-Ray will let you attack that. That's package dependencies. Here is Azurus, which is an open source BitTorrent client. And there's a whole lot of coupling going on here. But you can also filter these down, which is really useful in any kind of visualization tool like this to avoid the hairball effect. Filter it down so that you just see the really important connections that exist. It's going to be interesting to see what this looks like. This is from a real monolith that I did some work on. Yeah, you can't miss the lines on this one. This is from an actual project that I've been doing some work on, and no matter how bad the contrast is, you can't miss it here. This is the package level coupling on this project. The class level coupling actually crashed X-Ray, which is quite difficult to do, but they managed to do it. But even in this hideous mess, if you squint at this and look at it like an impressionistic painting, you definitely see hot spots here. You see a definite clustering up here and a different clustering down here, and that's really the structural hot spots within your code base. So if this were your monolith and you wanted to break this down into a smaller and smaller set of services, decompose it, eventually maybe into a microservice architecture, notice that when you look at each one of these packages or classes, the more red lines you have to snip, the harder your job's going to be. And the bolder those lines are, the harder it's going to be to snip them. And so you can look at this structurally